Welcome back, deep divers. We're about to embark on a truly essential deep dive today. One that, well, it underpins almost everything we do in our information-dependent world. Think about it. We live in this on-demand era, right?
Yeah.
We expect information instantly.
Instantly, yeah. Sharing photos, streaming.
Exactly. Streaming video or even just checking email. But have you ever truly considered where all that information actually lives?
Well, it's fascinating how personal data, stuff created on our phones and laptops, it just explodes in value the moment it's shared and uploaded to central repositories.
Right.
And this leads us to a fundamental challenge. How do we manage this ever-growing ocean of digital information? Make it accessible, keep it secure, make it useful.
That's precisely our mission today. We're taking a deep dive into the data center environment with a laser focus on its most critical component, storage. We've pulled together a pretty comprehensive stack of sources to guide us so you'll understand everything from the raw bits to the most sophisticated systems keeping your data available, secure, and ready for action.
Yeah, and we'll trace the evolution of storage, explore the core elements that make a data center tick, and unpack groundbreaking technologies like virtualization and cloud computing. They've completely reshaped how we think about and interact with data.
Definitely.
Get ready for some genuine insights, I think.
Okay, so every day we're creating this tsunami of data. But what is this raw material, really? And how does it transform into something meaningful, something we can actually use?
That fundamental distinction is really where our deep dive begins.
Yeah.
Data is simply a collection of raw facts. Think of it as like unstructured pieces, handwritten letters, a single photograph, maybe entries in a bank ledger.
Just raw stuff.
Exactly. Information, on the other hand, that's the intelligence, the knowledge we derive from that raw data. It's what happens when you analyze those bank ledger entries, spot meaningful business trends, or extract insights from a bunch of photos.
Giving it context.
And this distinction became even more critical with the explosion of digital data. If we connect this to the bigger picture, this wasn't just gradual.
No, it felt sudden.
It was a sudden, massive surge. Three forces primarily drove it. First, the ability to process and convert vast amounts of content into digital formats. Second, the constantly plummeting cost of digital storage.
Oh, just huge.
Absolutely. And third, surprisingly affordable, light and fast communication technology. Just compare sending an email now to relying on snail mail a few decades ago.
Oh, yeah. Totally different world.
It's a completely different world. This explosion, in turn, led directly to the concept of big data. These data sets so enormous, so varied, dynamic, and complex that, well, traditional tools just couldn't handle them.
Could keep up.
Not at all. And from that challenge, a whole new field emerged. Data science, which is a powerful blend of stats, math, data visualization, computer science, all focused on extracting real business value from these vast information oceans.
So all this data needs a home. What is a data center at its core?
Well, essentially, it's a specialized facility. It provides centralized data processing capabilities for enterprises, specifically designed to house and manage massive amounts of information.
Right.
Its infrastructure isn't just rows of computers, It includes all the essential hardware servers, storage, network devices, plus critical components like robust power backups.
Can't forget the power.
Definitely not. Then there's the extensive software layer apps, OSs, sophisticated management tools, and the environmental controls. Precision AC, advanced fire suppression, just as vital.
Yeah, keeping it cool and safe.
And many large organizations even maintain multiple data centers, not just to spread workloads, but crucially for disaster recovery. Ensures business continuity even if one site goes down.
So given that, what are the foundational building blocks that truly make a data center functional? What makes it tick?
Our sources highlight 5 core elements, and they really have to work together, like a symphony.
Okay.
First, the application, that's the actual computer program, the logic for your business operations, like an online order processing system.
Got it.
Second, the database management system, DBMS, which gives us a structured way to store and manage data, usually in interrelated tables.
The database itself.
Exactly. Third, the host or compute system. That's the platform, the hardware, firmware, software that actually runs those applications and databases.
Where the work happens.
Right. Fourth, the network, acting as the crucial data path, facilitating lightning-fast communication among all these devices.
The connections.
And finally, storage, which is the device responsible for persistently retaining all that data. So, imagine placing an online order. A customer uses their device, connects to a host running an app. The app accesses the DBMS. The DBMS writes the order data to physical disks in a storage array, all communicating efficiently via the network.
Okay, that makes sense. And what makes a good data center, especially when we're zeroing in on storage?
Well, there are several key characteristics that apply across the board, but
Yeah.
they are absolutely vital for storage systems. First up, availability.
Had to be there.
Information must be accessible exactly when you need it. For some businesses, an hour of unavailability. It can cost millions. Second is security. Robust policies, procedures to prevent any unauthorized access. Then, scalability. As your business grows, its resources must expand seamlessly without interrupting things.
Goes with you.
Exactly. Performance is next. Optimal speed and responsiveness based on predefined service levels. Don't forget data integrity, using things like error correction codes to ensure data is stored and retrieved exactly as received, no corruption.
Gotta trust the data.
Have to. Capacity ensures you have adequate resources, efficient storage, and processing. And finally, manageability. Easy, integrated management, often through automation to reduce human error and manual effort.
Okay, so achieving all that, it's not just a set up and forget thing, is it?
Not at all. It demands ongoing management activities. Monitoring is key, a continuous process, gathering real-time info on security, performance, availability, capacity.
Keeping an eye on everything.
Constantly. Then there's reporting, generating periodic summaries on resource performance, capacity, utilization. These reports are invaluable for, say, justifying investments or for chargeback attributing costs back to the departments using the resources.
Makes sense.
And underpinning it all is provisioning, the dynamic process of providing the necessary hardware, software, other resources to meet those evolving capacity, availability, performance, and security needs.
And this is where we see a real shift, right? How technologies like virtualization completely change the game for provisioning and managing these resources.
Absolutely. Virtualization is fundamentally about abstracting physical resources, compute, storage, network, and presenting them as logical ones. It's not brand new. We've seen forms like virtual memory or disk partitioning for years.
Right.
But what's so powerful about it now is its ability to pool physical resources. Instead of seeing a dozen individual storage devices, virtualization lets them appear as one single aggregated large storage entity.
One big pool.
Exactly. And this pooling isn't just neat, it's critical because it enables centralized management of those aggregated resources, simplifying operations and making them way more efficient.
So let's look at the specific types we see in data centers. What are they?
Okay, first, there's application virtualization. This breaks the dependency between an app and its underlying OS or hardware. It basically encapsulates the app and its required resources in a virtual container.
Like a little bubble for the app.
Kind of, yeah. It means you can deploy apps without changing the core OS, and it cleverly isolates applications, preventing conflicts.
Okay, what else?
Next, compute virtualization. This masks the physical hardware from the OS. It allows multiple operating systems, or virtual machines, VMs, to run concurrently on a single physical machine.
The magic behind that.
The hypervisor. It's a virtualization layer sitting between the hardware and the VMs, giving each VM its own virtual CPU, memory, network resources, all in a completely isolated environment.
Got it. And the third type?
Desktop virtualization. This tackles the traditional desktop model where the OS, apps, user profiles are tied to specific hardware. It frees them, allowing full desktops to run as VMs in the data center, accessed remotely.
So your desktop lives in the data center, not on your desk.
Precisely. Centralized execution and storage. It significantly mitigates data leakage risks, streamlines backup and compliance, and makes desktop maintenance much, much easier.
Okay, so we have data centers, virtualized environments. Now, the big question, how do these hosts actually connect to the storage devices? The plumbing, basically.
Right, the plumbing. It relies on both physical components and the communication protocols they use. Physical pieces are straightforward. You need a host interface device. That's typically an HBA host bus adapter for storage or a NIC network interface card for general networking.
HBA or NIC.
Yep. HBAs are often specialized chips, ASICs, that offload I/O processing from the main CPU, making things more efficient. Then there's the port, the specialized outlet for the connection, and of course the cable, copper, or fiber optic linking everything.
And what language do these devices use to talk to each other across these connections?
The protocols.
Yeah, we've seen a real evolution here. Historically, there was IDIATA, or parallel ATA. Common for disk drives, CD-ROMs, parallel transmission limited.
Old school.
Very. That largely gave way to SATA, serial ATA. Serial version, higher performance, lower cost, pushing speeds up to like 6 Graves now.
Much better.
Then for more demanding stuff, SCSI, small computer system interface, was preferred. Parallel, better performance, more devices. Then came SAS, serial attached SCSI, a point-to-point serial alternative, also hitting 6 Graves.
Okay.
For dedicated high-speed storage communication, fiber channel, FC, became the gold standard. Gigabit speeds over copper or optical fiber, now up to 16 Graves.
The really fast stuff.
Exactly. And increasingly, Internet Protocol, IP, the same protocol powering the Internet, is used for host-to-storage communication, especially in IP SANs.
So with all these ways to connect, how does a host actually access the data? Good question. There are a few key methods for how data is presented and retrieved. First, the simplest. Direct attached storage, DAS. Storage connected directly to a single host, like your internal hard drive.
Simple enough.
Then we move into network access. Here you have block-level access, which is incredibly efficient. The file system's created on the host, and data is accessed at the raw block level over the network. It's like assigning raw disks directly to that host.
Close to the metal, sort of.
Pretty much. In contrast, file-level access has the file system created on a separate file server or on the storage side. This generally involves higher overhead because data is accessed at the file level, requiring more processing.
More translation needed.
Right. And then there's object-level access, a more modern approach. Data is accessed over a network as self-contained objects, each with a unique identifier and its own metadata. Ideal for massive unstructured data.
So, okay, let's get down to the actual media where data physically resides. What are our options? Pros and cons?
Historically, we've relied on magnetic media disks, tapes, older diskettes. Then there's optical media like CDs and DVDs. And now, increasingly dominant is solid-state media, like removable flash memory and flash drives, or SSDs.
SSDs are everywhere now.
You really are. And it's fascinating to see how older tech had limitations that pushed us toward disks for enterprise use.
Like tapes.
Exactly. Tapes are inherently sequential access, super slow for anything but pure streaming. You can't just jump to a piece of data.
Have to wind through it.
Right, and data on tape couldn't be accessed by multiple apps simultaneously, plus the read-write head actually touched the tape, causing wear and tear, and the management overhead, significant. So they're largely not preferred for enterprise backup anymore.
And optical discs.
Similar story. Optical discs had limited capacity and speed, mostly for small single-user stuff. Their write once, read many worm feature was an advantage for fixed content, but overall limitations kept them out of the high-performance space.
So the king of storage for performance-intensive apps became
Disk drives. Hard disk drives, or HDDs. They support rapid random access, offer large capacity, and you can configure them in arrays for even more capacity and performance.
Let's unpack the anatomy of an HDD then. What's inside?
Okay, inside you find one or more flat circular disks called platters, coated with magnetic material where data is recorded in binary.
The spinning disks.
Yep, they're all mounted on a central spindle attached to a motor that spins them at thousands of RPMs, anywhere from 5,400 to a blazing 15,000 RPM.
Wow, that's fast.
It is. And then you have the crucial read-write, RW heads. These float on a microscopic cushion of air above the platter, reading and writing data without touching it.
Floating on air.
Literally. When the spindle stops, the heads safely park on a special landing zone. A head crash, that's the nightmare scenario. The head touches the platter outside the landing zone, scratches the coating. Usually means data loss.
Yikes. Okay, so what impacts the performance of these mechanical marvels?
3 key factors. First, seek time or access time. Time for the heads to physically move across the platter to the right track, measured in milliseconds, maybe 3 to 15 meters. You can even short stroke a drive, limiting its usable capacity to reduce seek time.
Keep the heads closer.
Exactly. Second is rotational latency. Time for the platter to spin until the requested data is under the RW head. Depends entirely on RPM. For a 15,000 RPM drive, average latency is about 2 milliseconds.
Tiny delays, but they add up.
They absolutely do. And third, the data transfer rate. Average data delivered per unit time to the HBA. There's an internal rate, platter to buffer, and an external rate, buffer to HBA. And here's a crucial insight for anyone managing systems: the impact of disk I/O controller utilization.
Utilization. This sounds important.
It's critical. Imagine the I/O controller as a bottleneck.
Yeah.
Request queue up. If the controller gets too busy, that queue gets huge and response time skyrockets.
Goes through the roof.
Literally. The formula is roughly average response time equals service time. 1 utilization. As utilization approaches 100%, response time approaches infinity, your system grinds to a halt.
Not good.
Definitely not. That's why keeping disk utilization below 70% is non-negotiable for performance-sensitive apps. It saves you from that exponential cliff where a little more demand leads to an infinitely long wait.
It really highlights the balancing act. So how do you figure out how many disks you actually need? It's capacity versus performance, right?
Exactly. It's a balance. You
Yeah.
calculate the max IOPS, input-output operations per second, a drive can handle. But like we said, for sensitive apps, you calculate based on that 70% utilization rule.
Can you give us an example?
Sure. Say you need 1.46 terabytes capacity and 9,000 IOPS. You have 146 gigabytes, 15,000 RPM drives, each capable of 180 IOPS max.
Okay.
For capacity, 1.46 TB divided by 146 gigabytes, that's 10 disks. Simple.
Right.
But for performance, at 70% utilization, each drive delivers 0.7, so 126 IOPS realistically. To get 9,000 IOPS, you need 9,000 divided by 126. That's 72 disks.
Wow. Big difference. 10 versus 72.
Huge difference. And the organization needs the maximum of those, so 72 disks. Performance often drives the requirement way higher than just capacity.
Okay. So that example shows the challenge with mechanical disks. Is there an alternative to just adding more and more HDDs for high I/O?
Absolutely. Enter flash drives or SSDs, solid-state drives.
The non-moving parts ones.
Exactly. Their benefits are huge. Ultra high performance because no moving parts means zero seek or rotational latency. Low power consumption, too.
About IOPS.
Massive IOPS, with response times typically under 1 millisecond. Ideal for small block, random read workloads, think currency exchanges, real-time data feeds.
But they cost more per GB, right?
Upfront, yes, but they often provide a better total cost of ownership, TCO. You need far fewer drives, maybe 20 to 30 times less than HDDs for the same performance.
Ah, okay.
That translates directly into savings on drive cost, power, cooling, space, and even management.
Makes sense. So given how critical data is, we need protection against disk failures. That's where RAID comes in, right? Redundant array of independent disks.
Precisely. Disk drives fail. It's mechanical. The more disks you have, the higher the probability of a failure in the array. Like 100 disks, each lasting 750,000 hours on average. You might expect a failure every 7,500 hours in that array.
That often.
Statistically, yeah. So RAID provides both data protection and can enhance performance.
So what are the core techniques behind RAID?
It's fascinating, really. 3 fundamental building blocks underlie all RAID levels. First, striping. Spreading data blocks across multiple disks. Great for performance read-write simultaneously across drives.
Faster I/O.
Much faster. Second, mirroring. Keeping 2 identical copies of data on separate disks. 100% redundancy. If one disk fails, you have a perfect copy.
Costly, right? Needs double the disks.
Exactly. 100% overhead. And third, parity. A clever mathematical construct, often using XOR, that lets you recreate missing data from a failed disk without full mirroring.
How does that work?
Parity info is stored on an additional disk or distributed across disks. It reduces costs significantly, maybe 25% extra space for 4 data plus 1 parity. But calculating parity during writes can sometimes impact performance.
Okay, striping, mirroring, parity. How do these combine into the different RAID levels we hear about?
Right, let's unpack the common ones. RAID 0 striping. Stripes data across all disks. Max capacity, max performance. But 0 data protection. 1 disk fails, all data gone.
High risk, high reward, sort of.
Pretty much. RAID 1 plus 0, RAID 10 striped mirror, combines RAID 0 performance with RAID 1 redundancy. Data is first mirrored, then those mirrored pairs are striped. Needs an even number of disks, minimum 4. Excellent for small, random, write-intensive IOs like OLTP databases.
That's expensive again.
Very high cost due to mirroring. RAID 5, striping with distributed parity. Very versatile, widely used. Key is parity is distributed across all disks, overcomes the right bottleneck of a dedicated parity disk. Good for random, read-intensive applications messaging, RDBMS.
A good all-rounder.
Often, yes. RAID 6, dual distributed parity. Similar to RAID 5, it adds a second parity element. This is huge, allows survival if 2 disks fail in the set. Needs at least hair disks.
More protection. Any downsides?
Higher write penalties, more overhead for writes, and potentially longer rebuild times in RAID 5. But that dual disk failure protection is significant.
Okay, so different levels, different trade-offs. How do you choose the right one? Let's look at those scenarios you mentioned.
Right. Scenario 1. Telecom companies, 730 gigabit data, 5 by 200 gigabyte disks in RAID 0, 15% random writes, 85% random reads. Crucial constraint. No budget for new disks.
Okay, what do they do?
Well, 730 gigabyte fits on 4 of their disks capacity-wise. Since they need protection and can't buy disks, parity base is the only option. RAID 3 is for sequential, doesn't fit. So RAID 5, 4 data plus 1 parity, fits on their 5 disks and handles the read-write profile reasonably well.
Recommendation, RAID 5, pros and cons.
Pro, low-cost data protection using existing hardware. Con, high overhead during rebuild. If a disk fails, potential performance hit then.
Got it. Scenario 2, same company, new budget. 900 gigabyte of data growing to 1170 gigabytes, 6 by 200 gigabyte disks in RAID 0. Now, 40% write operations, new disks cost $1,000 each.
Okay, 1170 gigareads needs 7 disks capacity-wise, but 40% writes, that's high. Parity RAID, like RAID 5, will likely suffer performance-wise due to parity calculations. RAID 1 alone won't give enough capacity.
So what's the recommendation?
RAID 1 plus 0. It excels in high-rate environments. Needs 7 disk pairs for 1170 gigaready, so 14 disks total. They have 6, need to buy 8 more. Cost $8,000.
Advantages. Disadvantages.
Advantages. Excellent protection, very good performance for high writes. Minimal disruption on disk failure. Disadvantage. Highest cost due to 100% mirroring.
Okay, makes sense. Moving beyond basic RAID sets, let's talk about intelligent storage systems. Sounds advanced.
They are. These are feature-rich RAID arrays designed for business-critical apps needing top performance, availability, security, scalability. They pack large caches, multiple I/O paths, sophisticated algorithms to optimize I/O.
And they support newer tech, too.
Absolutely. Full support for flash drives, virtual provisioning, automated tiering, adding new dimensions to their capabilities.
So what are the key components that make these intelligent systems work so well?
4 key pieces working together. First, the front end. Interface between the storage system and the host. Redundant controllers, multiple ports. Executes protocols like FC or ISCSI. Routes data to from cache, acknowledges writes back to the host quickly.
The connection point.
Right. Second, cache. High-speed semiconductor memory, temporary data store, dramatically improves performance by insulating hosts from slow mechanical disk delays. Access is sub-millisecond from cache. Writes typically hit cache first, then go to disk.
Speed booster.
Definitely. Third, the backend. Interface between cache and physical disks. Controls data transfers, communicates with disks, provides error detection correction, RAID functionality, often dual controllers, multiple ports for high availability.
Manages the disks.
Yep. And finally, the physical disks themselves. Persistent storage can be a mix FC, SATA, SAS, flash drives, often within the same array.
That cache sounds crucial. How specifically does it make things faster beyond just being a buffer?
Good question. One technique is prefetch, or read-ahead. For sequential reads, the system anticipates future needs and reads blocks not yet requested into cache in advance.
So the data's waiting.
Exactly. Lightning-fast response. Another powerful example is server flash caching. This uses intelligent caching software plus a high-speed PCIe flash card installed on the host server.
Cache on the server itself.
Right. Dramatically improves app performance for read-intensive work nodes by cutting latency and offloading the back-end storage. Works in physical and virtual environments, intelligently caching what's needed most.
Okay, we understand these intelligent systems. How do we actually assign that storage to hosts? Provisioning, right?
Exactly. Storage provisioning. 2 main ways, traditional and virtual.
And virtual is the newer, more efficient way.
Generally, yes. It significantly improves on traditional methods. In traditional provisioning, LUNs, logical unit numbers, are created from a RAID set assigned to hosts. Host sees a raw disk, formats it.
Seems straightforward. What's the problem?
Inefficient capacity utilization. You allocate large chunks, but apps often don't use it all, leading to wasted space. Like allocate 1.5 TB, maybe only use 100 gigabit, but that 1.4 TB is tied up.
Stranded capacity.
Exactly. Virtual provisioning, or thing provisioning, leverages virtualization. Physical storage is not fully allocated up front when the thin LEON is created.
How does it work then?
Physical storage is allocated on demand from a shared pool of physical capacity. That pool can be large, even heterogeneous.
Benefits.
Dramatically improves utilization. That 1.5 TB allocated but unused in traditional suddenly becomes available space for new apps. Simplifies management, reduces power acquisition costs. Great when forecasting space is hard.
Any performance impact?
Can improve due to striping across many drives in the pool, but can also degrade if multiple thin LUNs heavily contend for shared resources, especially at high utilization.
Okay. As organizations grew, DAS became limiting. This led to storage area networks, or SANs. What problem do they solve?
They address explosive information growth, the need for 247 availability, and the demand for flexible, resilient infrastructure. FC SANs using Fibre Channel are a prime example, high-speed dedicated data transfer between servers and storage.
So it's a separate network just for storage.
That's the key idea, a dedicated high-speed network just for storage traffic, freeing up your main LAN. Core components include nodes, hosts, storage arrays, node ports, physical interfaces, cables, interconnecting devices, FC switch hubs form in the fabric, and SAN management software, purpose-built for speed and reliability.
So in this specialized SAN, how do devices identify themselves and communicate? Must be precise.
Very precise, like a dedicated postal service for data. Every device gets a permanent 64-bit unique identifier, a worldwide name, WWN, think MC address for storage, two types, WWNN node and WWPN port.
Okay, unique ID. Then what?
When it logs in, it gets a dynamic 24-bit FC address, like an IP address. A name server in the SAN tracks the mapping between permanent WWNs and temporary FC addresses.
And the language?
The Fibre Channel Protocol, FCP. Basically, SCSI commands over an FC network. Lets your server talk to remote storage like it's local, incredibly fast. Data is sent in fundamental units called frames addressing. Payload, SCSI data, checks them for integrity.
How do devices initially join and interact? You mentioned fabric services and login types.
Right. FC switches provide common services at predefined addresses. The Fabric login server handles initial login. The name server manages registration and discovery of node ports. The Fabric controller distributes change notifications, RSCNs. The management server lets management software administer the Fabric.
And the logins.
Three main types. FLOGI, Fabric login. Node port logs into the Fabric via a switch port, gets an FC address. PLOGI, port login, between two node ports to establish a session, PRLI, process login. Also between two node ports exchanging application-level parameters, like for SCSI.
So how are these switches connected? The SAN topologies?
Good question. You have mesh topologies, full mesh, every switch connected to every other, good for small numbers, 4 switches, max 1 hop, but uses lots of ports for interswitch links, ISLs.
Limit host ports.
Right. Partial mesh, more scalable, fewer ISLs, but traffic might take several hops, more complex management, potential ISL overload.
What's the alternative for larger environments?
The core edge fabric topology, 2 tiers, edge tier. Less expensive switches for adding hosts, connect to core via ISLs, core tier, high availability directors where storage devices connect directly.
So storage is central.
Exactly. All host-to-storage traffic hits the core, ensuring single-hop storage access from there. High-performance hosts might connect directly to the core, too. Increases connectivity, conserves ports, simplifies expansion.
And within these SANs, you mentioned zoning for security and management.
Yes, critical feature. Logically segments node ports into groups, communication only allowed within the same group. Limits broadcast of RSCNs, change notifications, reducing fabric management traffic, provides crucial access control works with LUN masking to ensure only authorized devices communicate. Think VIP lounge for data.
How is it structured?
Hierarchical. Zone members, ports nodes grouped into zones. Zones grouped into zone sets, only one zone set active at a time.
Okay. And finally, how does virtualization extend into the SAN itself?
2 key ways. First, block-level storage virtualization aggregates LUNs from potentially different storage arrays into one unified pool, abstracts the physical storage, provisions virtual volumes to hosts.
The virtualization layer sits in the middle.
Exactly. Acts as target to hosts, initiator to arrays. Major benefit. Enables non-disruptive data migration. Handles back-end data movement. LUNs stay online even when migrating between arrays or data centers.
Powerful. And the other way?
Virtual SAN, VNS SAN, logically partitions a single physical SAN into multiple isolated virtual SANs, improves security, isolates data, scalability, reuse FC addresses, availability, disruptions contained, manageability, easier than building separate physical SANs.
Okay, we've covered how data lives and connects. Now, protecting it. Let's start with basic backup.
Right, fundamental. An additional copy of production data, purely for recovery from loss or corruption.
What are its main purposes?
Threefold, usually. Disaster recovery, restoring at alternate site. Operational recovery, restoring from routine loss like accidental deletion. And archival, long-term preservation, though CAS is more common now for fixed content archives. The backup window is just the period when the source is available for backup.
And the level of detail. Backup granularity.
Depends heavily on business needs RTO and RPO. How fast you need to restore, how much data you can lose. 3 main types. Full backup. Complete data, fastest recovery, but needs most storage time.
Everything.
Yep. Incremental backup. Copies data changed since last full or incremental. Faster backup, but longer restore. Needs last full plus all incremental.
Only the changes since last time.
Right. Cumulative differential backup. Copies data changed since last full. Longer than incremental backup, but faster restore. Needs last full plus latest cumulative only.
Changes since the last full.
Most orgs use a combination to balance backup window and recovery needs.
So how does a backup operation actually work? The architecture.
Key players involved. Central backup server initiates, coordinates, keeps a catalog. Backup client is the source of data. Storage node media server controls and writes data to the backup device. And the backup device itself is the target, tape, disk.
And the flow.
Server instructs client storage node. Client sends data to storage node. Storage node writes to device, sends metadata to server updates catalog.
And restore.
Admin initiates. Server tells storage node to mount media data read sent to client. Database restores often need extra log files for consistency.
Beyond the technical flow, what broader considerations shape a backup strategy?
RPORTO are paramount dictate frequency. Retention period, how long to keep copies, often compliance-driven. Backup media type impacts RTO, disk faster than tape. Granularity, as discussed. Optimal timing minimize disruption. File size number impacts speed. Compression deduplication saves space bandwidth. Data location, especially with distributed setups.
Anything else?
Oh yeah, server configuration backup, SCB, saves server profiles for rapid recovery onto dissimilar hardware. Can be a lifesaver.
And where does the backup happen in the network? The topologies.
Right, several ways. Direct attached backup. Storage node on client, device attached directly. Metadata over LAN. Freeze LAN, but not scalable for sharing.
Simple, but limited.
Yeah. LAN-based backup. All components on LAN, data over LAN can impact performance unless dedicated backup network.
Common, but potentially slow.
Can be. SAN-based backup, LAN-free. Backup device and clients on SAN. Data stays on SAN, only metadata over LAN. Ideal for sharing devices, high performance.
Keeps backup traffic off the main network.
Exactly. Mixed topology, combining LAN and SAN based on needs.
Makes sense. What about NAS environments? They have proprietary OS file systems, right?
Yeah, unique challenge. Few approaches. Server-based. NAS headset app server, client, storage node device. Overloads network cat server.
Inefficient.
Very. Serverless. Network share mounted directly on storage node. Better. Reduces hops and server load. But the best is NDMP, Network Data Management Protocol, industry standard. Data transferred directly from NAShead to backup device. Metadata to backup server. Reduces app server load, improves speed.
How does NDMP work?
Two main ways. NDMP, two-way. Data to locally attached device. Minimal network traffic. NDMP, three-way. Separate private network between NAS heads for data, metadata over public network. Useful for sharing devices among NAS heads.
So what are the actual targets for these backups today? Tapes still used?
Physical tapes. Less so for primary enterprise backup. Low cost but slow sequential access. Single app access. Wear tear. Environmental needs. Transport risk. Shoe shining.
Lots of downsides.
Yeah. Low-cost disks led to disk as backup medium. Much faster. Building on that is the Virtual Tape Library, VTL.
VTL, what's that?
Disk drives emulated as tapes to backup software. Huge benefits. No changes to legacy software, better performance, reliability, random disk access, faster backup recovery, no physical tape maintenance, easy install, instant mounts, rewinds.
Best of both worlds almost.
Kinda, yeah. Addresses the tape limitations while using disk speed.
With all this backup, redundancy must be a huge issue, right?
Oh, yeah.
Copying the same data over and over.
Massive problem. Waste storage, bandwidth, extends backup windows. That's where data deduplication comes in.
How does that work?
Identifies and eliminates redundant data. Only unique data is stored. Duplicates get replaced with pointers. Benefits. Less storage, shorter backup window, less network bandwidth, longer retention on disk.
Where does deduplication happen?
Two main methods. Source-based deduplication eliminates redundancy at the source before sending over the network, dramatically cuts network traffic, shortens window, adds some overhead on the client.
Dedupe before sending.
Right. Target-based deduplication occurs at the backup device, offloads the client, can be inline, dedupes before storing, less capacity needed, adds backup process overhead, or post-process, stores first, dedupes later, needs more initial storage, better for tight windows.
And this helps with remote offices.
Absolutely. Disk-based backup with source-based dedupe is very effective for centralizing remote office backups over WANs without huge bandwidth needs.
How does backup work specifically in a virtualized world? Backing up VMs.
Two main approaches for VM data: OS, app, config. Traditional backup. Either agent on VM, VM looks like physical server but doesn't capture VM files, needs manual VM recreation, or agent on hypervisor. VMs look like files, backs up VM files, simpler but high CPU load on hypervisor.
Neither sounds ideal.
They have drawbacks, which leads to image-based backup. Operates at hypervisor level. Takes a snapshot of the entire VM, guest OS data state config. Saves a single image file. Image mounted on a proxy server, which acts as backup client, offloading the hypervisor. Enables quick, full VM restoration.
Much cleaner.
Generally preferred now.
Okay, what about data that's old but still needs to be kept? Archiving.
Right, data archiving. Key concept is fixed content data that ages, becomes less likely to change but still accessed. X-rays, CAD, financial docs, fastest growing sector.
So an archive is
A repository for this fixed content.
Right.
Meets regulatory compliance, supports new revenue strategies, can be online, immediate, nearline needs load, offline, manual.
What were the challenges with traditional archives?
Womb devices, optical tape, were cheap, but had high operational overhead, not optimized for duplicates, wear-tier issues, technology changes.
So the modern solution.
Content address storage, CAS, disk-based archive, better accessibility, protection, SLAs. The architecture usually involves an archiving agent. On app server, scans, sends data, leaves a stub file, an archiving server, policies, receives data, and an archive storage device.
Use cases.
Email archiving overcomes quotas, saves primary storage, long-term access. File sharing archiving moves old files, saves primary storage, long-term access.
Okay, beyond backup, we have replication, making copies for immediate use availability. Let's start with local replication.
Right, replicating data within the same array or data center. Uses: alternative backup source, zero backup window, fast recovery, decision support, analytics on copy, testing platform, data migration.
Key characteristics.
Recoverability, restore from replica, restartability, restart ops using replica, and crucially, consistency. Replica identical to source at a point in time, often needs dependent write I/O. Can be point in time, PIT, or continuous.
What are the host-based techniques for this?
One is LVM-based replication, LVM mirroring. The logical volume manager mirrors data across physical volumes. Writes go to both. Mirrors can be split.
Okay, another?
File system, FS, snapshot. Pointer-based replica using copy on first write, KFFW. When snapshot created, bitmap tracks changes on production FS. When a write hits production after snapshot, original data moved to snapshot space first, then new data written to production. Reads check bitmap if changed, read from snapshot. If unchanged, read from production.
Clever. Only copies what changes.
Very efficient. Similar idea is the save location mechanism in arrays. Write hits source original data copy to save location. New write happens. Target view combines unchanged source plus changed data from save location.
How do you keep these replicas synced or restore efficiently?
Incremental resynchronization restore. Uses bitmaps. Bit represents a block. Block changes bit flagged. When sync and restoring, logical OR on source target bitmaps identifies all changed blocks, only copy changed blocks. Much faster.
And replication in virtualized environments. VM snapshots.
VM snapshot captures state and data of a running VM at a point in time. Disks, memory, power state. Uses separate delta file for changes since snapshot. Useful for reverting VMs after logical corruption, bad patch, etc.
Limitations.
Doesn't support replication if VM uses raw disks. Too many snapshots can increase hypervisor load.
Now, remote replication protecting data at a distant site. Core modes.
Two main ones. Synchronous remote replication. Writes must commit to both source and target before host gets acknowledgement. Guarantees zero recovery point objective, RPO, no data loss.
Downside.
Performance impact due to latency. Typically limited to 100 kilometers. Needs dedicated high bandwidth links. If links fail, replication suspends. If source fails during link outage, RPO no longer zero.
Say, the other mode.
Asynchronous remote replication. Write committed to source, immediately acknowledged to host. Data buffered at source, sent to remote site later, provides finite, non-zero RPO, some data loss possible, eliminates performance impact on app response time, can span hundreds, thousands of kilometers, bandwidth provision for average load, buffers handle peaks, can optimize bandwidth using locality of reference.
How are these implemented?
Array-based remote replication, arrays manage it, primarily synchronous. Disk buffered replication, hybrid. Consistent PIT local replica created first, then transmitted remotely. Less bandwidth than pure sync-async. Network-based remote replication, continuous data protection or CDP. Write split local CDP appliance in production volume. Local appliance sends to remote appliance during journal volume. Allows recovery to almost any point in time in journal.
For ultimate resilience, some use 3-site remote replication. How's that work?
Cascade multi-hop, source intermediate bunker site, remote site, synchronous plus disk buffered, sync, source bunker, then PIT replica at bunker transmitted remotely, RPO typically hours, synchronous plus asynchronous, sync, source bunker, then async, bunker remote, bunker access source for async, RPO typically minutes. Good failover options.
And sometimes data is migrated between arrays over distance.
Yeah, data migration via push-pull operations uses a protection bitmap to track copied data. Host access to remote device usually blocked during operation, cold, or tracked carefully if online, hot, to ensure consistency.
Finally, remote replication for VMs, VM migration.
VM migration moves running VMs without powering off for BC or load balancing. Hypervisor to hypervisor moves active VM state memory disk control between hypervisors. Requires both hypervisors access the same shared storage. Array to array moves VM files, metadata, disk files from source array to remote array. Allows moving VMs across to similar storage. Tracks changes during replication. Good for performance capacity balancing too.
Okay, now the ultimate abstraction. Cloud computing. What's the core idea?
Usually built on virtualized data centers. Leverages resource pooling, combining IT resources, and rapid elasticity provision release capabilities quickly seems unlimited. Often supports multi-tenancy, multiple consumers sharing resources, driving down costs.
How are cloud services delivered? The service models.
Different layers of control, IaaS, infrastructure as a service, base layer, scalable compute capacity, VMs, storage. You deploy apps, don't manage underlying cloud infrastructure. Think Amazon EC2.
Renting the hardware basic OS.
Pretty much. PaaS, platform as a service, provides platform environment for app deployment. You control apps, not underlying infrastructure. Think Google App Engine, Microsoft Azure.
Renting the workshop.
Good analogy. Software as a service. You use providers' apps on their cloud infrastructure via web browser. Limited config control. Provider manages everything. Think Mozy Backup, Salesforce CRM.
Renting the finished product.
Exactly.
And how are these clouds deployed? The deployment models.
4 main types. Public cloud. Open use by general public. Owned by provider. Low capital cost, huge scalability. Risks. Less control, security, performance variability. Private cloud. Exclusive use by one organization. Can be on-premise, full control, high capex, or externally hosted. Community cloud. Exclusive use by specific community with shared concerns, e.g. government. Cost spread, potentially higher privacy security than public. Hybrid cloud. Mix of 2 or more clouds, private, public, community, linked by tech allowing portability, cloud bursting. Deploy less critical apps publicly, mission critical privately.
Best of both worlds, maybe.
Potentially, yes. It's very popular. Need to understand the cloud infrastructure layers, too. Physical infrastructure, server storage networks, virtual infrastructure, virtualization, resource pools, VMs, applications, platform, software for SaaS PaaS, cloud management service creation tools.
And storage in the cloud.
Cloud-optimized storage is designed for massive unstructured data growth. Scalable, flexible, elastic, global access on demand. Single access point leverages object storage with customizable metadata for intelligent placement, protection policies, built for scale and multi-tenancy.
So what are the challenges and considerations for moving to the cloud?
Challenges. Network latency impacts apps. Platform service compatibility, your app's SOS supported. Vendor lock-in, hard to change providers, API issues, migration costs, software licensing complexity.
But considerations.
Risk versus convenience, public for startups, hybrid for SMBs, private for enterprise control, application suitability, mission critical, often private, non-critical public, network intensive apps might struggle. Financial benefits, TTROI, CapEx versus OpEx, provider selection, history, ease of use, migration, security, compliance, support.
Okay, crucial layer now. Information security. No longer optional, right?
Absolutely critical. Storage is increasingly exposed. Need to protect vital info in traditional and virtualized DCs.
What are the fundamental security goals? The framework.
Built around the risk triad or CIA plus accountability, confidentiality, secrecy, only authorized access, via authentication, encryption, and transit trust, traffic flow protection, integrity, unaltered info, protect against unauthorized change deletion, error detection correction too, availability, reliable, timely access for authorized users, protect against DOS attacks, unauthorized deletion, sufficient resources, accountability, tracking actions, audit trails for non-repudiation, can't deny actions.
Common threats to these goals.
Data modification attacks threaten integrity, denial of service, DORAS attacks threaten availability, repudiation attacks threaten accountability.
How do we fight back?
Key concept. Defense in depth, Layered security, multiple measures. If one fails, others protect. Buys time to detect respond. Think attack surface, entry points, attack vector, path, work factor, effort to beat control.
Let's unpack the storage security domains, threats and controls.
Access paths categorized. 1. Application access. Apps access data over network. Threats. Spoofing user identity. Privilege elevation. Controls. User host auth. Authorization. ACLs. IRM. Network integrity. Storage network encryption. IPsec. FCSP. RBAC. Separation of duties. Physical access control. Encryption at rest. Secure data erasure.
Lots of layers there.
Has to be. 2. Management access. Admin access to storage devices. Threats. Spoofing admin identity. Elevating privileges. Controls. Admin access regulation auditing. Integrate with auth directories. LDAP, AD. RBAC. Separation of duties. Secure log files. 3. Backup, replication, archive access. Securing copied archive data. Threats. Tape loss theft. Unencrypted data on backup media. Controls. Encryption during backup. Secure media management.
How about specific implementations, SAN security?
LUN masking, host access to specific LUNs, zoning, logical segmentation, access control limits, RSCNs, FC switch port security, binding, lockdown, lockout, disable, ACLs, virtual SANs, VS, isolation, scalability, all part of defense and depth zones.
NAS security.
Permissions ACLs, Windows Unix, authentication authorization, Kerberos directory services, firewalls, multi-protocol permission mapping.
IP fan security.
Chemic Challenge Handshake Authentication Protocol is common for basic authentication.
And security in virtualized cloud. More complex.
Increased risk, multi-tenancy, less control. Need compute infrastructure security, secure physical servers, protect hypervisors, VM isolation hardening, network layer security, firewalls including virtual IDS, DMZ, data in flight encryption.
Finally, keeping it all running. Monitoring and management. Essential ongoing work, right?
Absolutely. Unprecedented growth demands efficient management. Need intelligent tools, robust processes, incident, problem, change requests to meet SLAs. Manage the entire infrastructure, not just pieces.
And monitoring is the foundation.
The bedrock. Provides performance accessibility status. Helps identify trends for capacity planning, forecasting, even HVAC monitoring. Key components. Servers, network, storage arrays, physical, virtual.
What parameters do you monitor?
Accessibility, hardware, software status. Capacity, available resources, free space, ports. Performance, efficiency, bottlenecks, IOPS, response time, utilization. Security, unauthorized access changes, login failures.
When things go wrong.
Alerting.
Critical. Informs admins about status, power disk memory switch failures. Alerts have severity. Information, useful, no action needed. Warning, needs attention. Fatal, immediate attention, impact likely. Continuous monitoring plus automated alerting, quick proactive response.
So what are the actual day-to-day management activities?
Broadly, availability management, redundancy RAID, clustering, replication. Capacity management, utilization, forecasting, planning, thin provisioning, helps. Performance management, efficiency, bottlenecks, tuning server volume, SAN ISLs, array layout. Security management, CIA plus A, access control, user counts, RBAC, zoning, LUN masking. Reporting, business justification, chargeback analysis.
Chargeback example.
Yeah, like calculating total raw capacity used by Payroll One app, including production volumes and space for its local remote replicas for accurate departmental cost allocation. Management in virtualized environments automates a lot of this.
What's the ideal solution for managing all this complexity?
Ideal solution correlates info from all components end-to-end view. Quicker root cause analysis, central monitoring management, multi-vendor support, notifications, automated scripts based on industry standards, SNMP, traditional but SMIS, storage management initiative spec, emerge for broader interoperability, policy-based management.
We're making sure data lives on the right kind of storage. Peering.
Right, storage tiering. Hierarchy of different storage types, tiers, based on SLA needs, performance, cost, protection.
Example.
High perf SSD SFC drives as tier 1, frequent access. Low cost SATA as tier 2, less frequent. Can be manual, complex, or automated, proactive monitoring, non-disruptive movement. Scope, intra-array within same array, or inter-array between arrays, often for archiving.
And the real value comes from?
Sub-LUN level tiering. Breaks LUNs into smaller segments, example 8 millib, allows much finer-grained movement of only the most active data to faster tiers. That's how you really optimize cost and performance. Put data where it needs to be, when it needs to be there. So we've truly taken a deep dive into the heart of data center storage today. from, the fundamental bits and physical components all the way up to the incredibly sophisticated systems that ensure our information is always there when we need it.
It's really incredible to consider how much thought, engineering, and, well, continuous innovation goes into keeping our entire digital world running seamlessly. We've covered everything from the intricate anatomy of hard drives and the resilience of RAID levels.
Yeah, all the way to cutting-edge cloud strategies and those intricate layers of security designed to protect it all.
Absolutely.
And, this journey doesn't stop here. The world of data storage continues to evolve at just an astonishing pace, driven by relentless innovation and, frankly, ever-growing demands.
So, what does this all mean for you, listening right now? How might understanding these underlying principles change the way you think about the digital information you create, consume, and rely on every single day? Well, that's it for this deep dive. Thank you so much for joining us on this fascinating exploration of data center storage. We look forward to our next deep dive with you.